thank you.
Okay, very good. Okay, so as Carol said, my name is Paul Avison. I'm a product specialist for JDSU here in the UK. So what I really wanted to do was to share some of the experiences that we've had with different radio operators and cellular operators around the world, and share some experiences we have with the testing side of that. So you'll get a couple of acronyms from us. So FTTA is fiber to the antenna. We also call it FTTWPE, so fiber to the worst place ever. Although the actual testing is not very difficult, and frankly, sewers are a bit less desirable. The environment that you have to test the fiber in it is pretty challenging. So it's right up at the top of the tower, and with all the safety problems that entails. So the agenda for today is just to look at some drivers and some of the challenges that face the testing of these new antennas and the fiber that goes to the antennas. We'll talk about the certification. Again, some new acronyms. FOCAT, FOCAT, stands for Fiber Optic Cell Acceptance Test. We'll talk about some troubleshooting, a couple of use cases that we've come across that were quite interesting. And we'll talk about a typical tool bag that people use, and then a very quick summary of what we've been discussing. So here is the obligatory what's driving growth slide that you probably see from many people. And the answer to what's driving growth is actually frankly, in a nutshell, it's my teenage daughter watching YouTube on her phone. So what we're seeing in developed parts of Europe already, in some countries, mobile penetration is over 100%. So there are more phones than people. And in the whole of Europe, in the whole of EMEA, you're looking at mobile penetration of 100% by 2015. And of those mobile phones, about 75% of those are going to be smartphones by 2015. So this requires a whole extra generation of base stations and very low latency and high-speed backhaul. So just to give you an idea, and this is a little bit US-centric, this slide, but to give you an idea of the 3G structure in North America, the LTE structure in North America, you're looking at something in the region of 15 megabits per second per sector. So 3 sectors in an antenna, so 45 megabits. And on average in the US, you're looking at 1,000 subscribers per cell site, or a third of those, 333 subscribers per sector. So each of those 333 subscribers is going to be sharing 15 megabits. So as we all start watching YouTube on our phones, downloading movies on our iPads on 4G, then it's going to require a whole, really an order of magnitude more cell sites. And the way the industry is likely to go is, as well as more sites, you're going to be seeing a lot more of the so-called small cells, the sort of the small radio infrastructure from people like Alcatel and Ericsson. So just to give you an idea of the problems that we have in where our office is in Basingstoke, where we are is really right on the edge of, even at 3G speeds, is right on the edge of coverage. So we are, although we're in nominally a high-speed area, we're fairly marginal where we are. So there's lots and lots of gaps, and this needs to be filled in and much higher speeds achieved. So depending on who you are, whether you're an operator or an installer, really, what are you most concerned about? Well, the first thing is profitability. One of the things that kills profitability is rework of installations. Also, if you damage equipment and damage cabling, that needs to be replaced. If you don't install things right first time, then there's maintenance costs. Delays can incur penalties. But also, if there are issues with cell sites, then one of the consequences is customer churn. So obviously reduced revenue per user. On the reliability side, we've seen an awful lot of fairly poor installs from people that are used to installing coax and are really not familiar with fiber. So we see bad practices, we see dirty connectors, we see macro bending, we see bends in the fiber. Micro bending is kind of pressure on the fiber. Macro bends are actual bends in the fiber itself. So again, what people will see is really a poor customer experience, and again, more churn, more outages. So on the deliverability side, again, when you try to turn up a cell, if you have a failure, then that leads to lots of delays, troubleshooting, things like that. There is a big dynamic at the moment. There is some people have a very aggressive deployment schedule. So lots of sites, very short time, and typically the workforce that is installing this is not, although they are skilled in certain areas, they're not used to fiber. So there's a level of training that's required. And then the final thing is liability. So who pays for the problems? So how do you ensure as an installer you protect yourself from the operator saying, well, you haven't done a very good job here, you need to come back and fix it. So those are really the dynamics of this kind of area. So what we're going to talk about today is really how to deliver efficient, reliable, and quality fiber to the antenna installations. So one thing is to improve efficiency and improve by using the right test tools and certify the work, so you have reliable, optimized installations. Minimize rework due to poor practices and obviously improve customer satisfaction, and upskill the team. So minimize the amount of training by using the right tools that can certify the work without requiring a huge amount of fiber knowledge and fiber experience. So there's an evolution going on in mobile networks, and really we're at the start of fiber to the antenna. So what we're seeing at the moment is, what we're starting to see in certain areas, is fiber replacing the coax cable going up the tower. And there are advantages to this. It's lower loss, it's far better performance, it's much higher speeds. It's much easier to install, so it's lighter. But what it also allows, it also allows the remote radio head to be located next to the antennas. So that gives you a better signal to noise ratio because they're together, they're not separated by 40 meters of coax, and it allows the baseband unit to be optimized for size and really conveniently located at the bottom of the tower, or even remotely with some of the new installations we're seeing. So it's a pretty simple network. You're looking at on the tower itself, you're looking at a junction box. Well, from the baseband unit, you're looking at a jumper into the junction box. Then you've got the multi-fiber trunk cable up the tower, another junction box, and then a jumper from the junction box into the antenna. So it's a pretty simple network. So what it actually looks like in practice is this. So on the bottom right, this is the baseband unit equipment, and then top right you've got the junction box inside the tower, and then on top left you've got the weatherproof housing for another junction box, and then the antenna itself. So one thing that does come out of this is, although we do see some hardened connectors, most of the installations that we see have a weatherproof housing, and they have fairly standard telecom connectors in here. So this one is, if you look at the top right, you're looking at standard LCPC connectors. So nothing unusual here at all, but in a weatherproofed housing. So in terms of the typical solutions, what people are using to certify these fiber networks up the tower, Again, in number order, and people are typically using an OTDR, so an optical time domain reflectometer. And I'll talk a little bit more about this in a couple of minutes. They're using inspection scopes. So there's a very typical example of an inspection scope and a power meter to look at the actual connectors themselves and look at the power of the signal that's coming in at particular points in the small network. You're looking at light sources to inject some light into the fiber, and then we've also recently developed some power meters that, as well as having the power meter itself, they're also able to take an input from a digital microscope, and you can inspect connectors, but also pass-fail connectors according to a standard, then store the image and store the report and certify that this particular connector has so much power coming out of it, and the connector end face looks like this. Moving on to the transport side, a typical troubleshooting tool would be a tester like this, an MTS 5800, which has the Fibre type transport layer, or also OBSAI as well, which is another standard that we see mainly abroad. So at the bottom of the tower, you would typically use an OTDR. You'd need to inspect your connectors. You check the power, you check the loss of the fiber link, and the VFL would be the VFL is a visual fault locator, which is a red laser, and just use that to make sure that you've got the right fibers connected to the right devices at the bottom and the right antennas at the top. So just a very simple continuity test. At the top of the tower, the key things are to inspect the connectors and certify those connectors as well. So on the right-hand side, we've also got a picture of a very small pocket visual fault locator, and bottom right, you've got a microscope, a digital microscope connected to a PC that can inspect connectors and certify that they are good. So we're seeing a new dynamic in cellular towers, and we call this Flowchart certification. So this is a fiber optic cell acceptance test, and we're seeing a lot more people, as they're starting to deploy fiber to the antenna, they're starting to really be quite careful about how they deploy fiber and how they certify it to minimize the amount of rework they have to do. So I'll show this in a couple of examples towards the end. So we separate this really into two areas. So the Tier 1 certification is the simpler one. So the first thing to do is check the fiber continuity. So use the visual fault locator to check that if you put light in one end, you actually get red light coming out of the other end. You check and certify the connector end face for every component up the tower, from the bottom right to the top and then back down again. You check the power levels of the active equipment. So you check the output of the SFPs at the bottom and the top. And then you check with a source and a power meter, you check the total loss of probably 2 or 3 connectors, and you might want to do a loop back at the top and measure all the way up the tower and then all the way back down again. So that's the Tier 1 test. The Tier 2 test includes an OTDR. So an OTDR is a more sophisticated tool. So the first thing to do, check the fiber continuity again. Again, probably most importantly and most vulnerably, check the connector end faces and certify those. And then with the OTDR, you can measure the length of the fiber that you have, and you should know exactly the length of the fiber that you have. If you have a different length, then you have a break somewhere. And then what the OTDR can do is it can measure the discrete losses of all the individual lengths of fiber, and also all the connectors or joints up and down the tower. So it's a more sophisticated equipment, and I'll show you some pictures in a couple of minutes. So what are the causes of network failure? Well, we quite like this this graph, and we do show it a lot. But the question is, or the question that was asked here, what have you seen that has caused a network failure? So the number one cause of network failure is connectors. So it's contamination of the end face or damage to the end face. But one of the other things that we've seen is also key in this area, the fiber to the antenna, is the bottom one actually, which is excessive bending of the cable. So if you've got a mixture of, you've got a perfect storm, if you like, of people that are not particularly experienced in using fiber, and an environment where you have to clamp cable and bend cable around corners. So if you have excessive bending of the cable, it can easily take the link down. So I mentioned that bad fiber connections cause 80% of fiber faults. We are in this environment, FTTA. It's a bit of a mixture of single mode and multi-mode, depending on who you talk to. But more typically at the moment, we see single mode. So with single mode fiber, even a single particle on the core of the fiber. So the core of single mode fiber is 9 microns. Typical piece of dirt is something in the region of 4 to 6 microns. So it's a very large part of the core. So even if you have a single particle on the core, it causes back reflection, which can destabilize the lasers, causes insertion loss, and also it can damage the connector. So if you have a bit of dirt here, excuse me, a bit of dirt on the core, you get back reflection, and the light that's reflected obviously doesn't go through to the other connector and will cause loss in the link. One of the key points here is that if you mate a connector when it's dirty and you try to clean it, once you remove the debris, you get defects in the connector or in the fiber in the connector. So these pits and chips cause reflection. They also cause insertion loss and problems further down the line. The problem that most people have, and this is what I'll talk about in the use cases, is that most connectors are not inspected until after people find a problem. So they find that they have a problem with the installation, they go and check all the connectors, and they find that the people that have put the network together have just mated the connectors without any inspection or cleaning. And at that point, they've already damaged permanently the connectors. So just to give you a quick idea of what happens when you mate a couple of you mate a connector with a couple of pieces of dirt on it. So what people often do is they try a connection, and if it doesn't work properly, they maybe take the connector out and put it back in. What actually happens there is if you have there's quite a scientific there's been some quite scientific studies involved in what happens to dirt when you make connectors. And what's been found is that the size of the dirt particle has a very big effect on what happens. So particles that are 5 microns or less tend to be pushed into the glass and tend to stay there. They embed themselves in the surface. Particles that are bigger than 5 microns tend to be they're too big to be pushed into the glass. They tend to just break up and spread themselves over the end face. So if I make this connector a couple of times, what you end up with is smaller particles that are now spread across the end face. So you started off with a couple of big particles away from the core, and just mating the connector 3 times, you ended up with lots of small particles. In this case, you've got the core is completely excluded. So this connector does not work, and because of the damage from the embedded dirt, it will likely never work. So the question then is, where does the contamination come from? So the contamination is all around us. So there's dust in the environment. It's really a percentage game. you need, one of the best things to do is to inspect and clean just before you make the connection. So then you have the least possibility of getting dirt from the environment onto the end face of the connector. One of the other key areas for getting dirt on the end face is from test equipment. So test equipment, what people typically do, they have a piece of test equipment, maybe an OTDR, they have a test lead, and the test lead isn't inspected and cleaned. They plug the test lead into the network, and the test lead is damaged or it's dirty, and they then damage and make dirty the network they're trying to measure. So it's a bit of a vicious circle, really. Okay, so this just gives you a quick idea of what an OTDR trace with a dirty connector looks like. So the number 1 and also number 2 are quite good connectors. They're clean, and we're getting a nice loss of maybe 0.2 dB back reflection in the minus 60 dB area. So very good connectors. Number 3 has a small piece of dirt on the core, something in the region of 4 to 5 microns, and that's giving us a loss of about 5 dB. So that's 3/4 of the light is being thrown away in this particular example. So a very simple process to fix this. First thing to do is inspect. If it's clean, well, if it's not clean, then you clean it and inspect it again. If it is clean, then you go ahead and connect it. Really simple flowchart, but you need to make sure you apply this to both sides of the connection, because the bulkhead side is much more likely to be contaminated than the patch cord side. It's harder to clean, it's harder to inspect, so people tend to neglect it rather more. And then last couple of slides on inspection. And this is probably the most important, is it's much more important to be proactive with inspection rather than reactive. So it's very easy to clean connectors before they're mated and before you've embedded the dirt into a connector. So this is a dirty fiber prior to mating, and at this point you can just clean it without any problems. Pretty much anything will work. Nothing sophisticated, just a T-top or a one-click cleaner or something like that. The problem is what most people do is they are reactive, and they have a dirty connector like this, and at this point it's easy to clean. But if they connect it and try to clean it many, many times, what they're left with is damage. And because the end face is a dome, the pressure is concentrated in the center of the fiber, therefore on the core, so you're more likely to have damage on the core than anywhere else. So that's why it's most important to be proactive rather than reactive with inspection. And then just finally on inspection, there are standards for connector quality. And the main standard that's being used right now is an IEC standard, and it's snappily called IEC 61300-3-35. And it sets standards for, it's an interoperability standard, so it sets standards for the handover of interfaces from a supplier to a customer, whether that's a supplier of cables to their customer, or whether it's an installer of patch panels or networks to their customer. So it's a handover standard. And what's also important in this environment is to be objective about the inspection. So the connector on the bottom left, is this a good connector or is it a bad connector? Well, if you actually subject this to the standard, what you'll find is there's actually there's enough defects on this to fail the standard. So you can, with a digital microscope, you can set the standards any way you wish, but a good place to start is the IEC standard. So probably the next most vital test, considering a lot of the problems that we see are just due to people connecting the wrong fiber to the wrong hole, is a visual fault or a continuity test using visual fault locator. So VFLs are generally just a red laser at either 630 or 650 nanometers. The lower the wavelength, typically the brighter they are to the eye. And it's just used to just check fiber locations and just detect faults due to bending. So if you have a bend in a sort of yellow jacketed fiber, you can see the light coming out the side of the fiber, and just to confirm the continuity as well. So these are typically either just a small handheld unit, or often they're built into a mainframe. Okay, so bending. So bending is one of the other things that, or one of the other issues that you'll often see with fiber installs, particularly when people are inexperienced. So that it kind of splits itself up into two areas. One is micro bending, so that's caused by problems in the core cladding interface. So this is a smaller effect than macro bending, but it can be significant when you get poor conditions in the or when you get a poorly designed cable or problems in the fiber itself. Macro bending is the one that we see the most, and it's the most significant. So it's caused by physical bends in the fiber. So when you exceed the bend radius, when you exceed the minimum bend radius of the fiber, so to put it bluntly, the fiber just escapes out of the side of the core. It is a wavelength sensitive effect. So fiber is much more sensitive at, say, 1550 than it is at 1310. So if you have an OTDR that has, say, 2 wavelengths, a macro bend will show up. It should show up automatically because the loss of that particular event will be higher at the higher wavelength. Okay. So Tier 1 certification. Really, this is really the toolkit that people are using for this. So at the top of the tower, there's a bit of a choice of either analog inspection. So these are handheld devices that you can just it's a subjective picture of the end of the connector. So you look at the end of the connector and you say, is that good or is that bad? And there's also a power meter built into these units as well. On the right-hand side, you've got a digital microscope, so it does the same job. It has a power meter, it has a microscope connected to it, but it gives you a report of the condition of the connector and the power that's coming out. And what you'll often see as well at the top of a tower is people install a loopback on each fiber pair, so they can do a test, a loss test from the bottom of the tower through the loopback at the top, and then into a power meter at the base. So at the bottom of the tower, what you'll often see is a digital microscope, so to record the end face and create a report, a light source, power meter. That power meter might be one of those small ones on the left-hand side, so which is a USB power meter, so you can certify the loss of the link. And then, of course, on the right-hand side, you've got the visual fault locator and cleaners. And one thing that we found that's really important in particularly on the top of the tower side, is just the ability to do this hands-free. So things like neck straps, cases, you can hang these around your neck and actually do the testing without actually having to hold the equipment. So that's been very important for people that we've been selling these units to. So one of the most important things at the bottom, once you've done the fiber connector certification, is the insertion loss measurement. So this is just purely a measurement of the power drop across the entire link. So typically this will be done on a fiber pair. So the loopback will be installed at the top of the fiber pair at the top of the tower. You'll have the source attached to one side of the link, and you'll have the power meter attached to the other side of the link, and you'll measure the total loss of all the events, which includes the cable, the connectors, all the dirty connectors, all the bends, That'll be summed into a single number. It does not give you any information about individual events. That's the job of the OTDR. So if this is okay, if the link is has a good loss value, then you often don't need to move on to the tier 2 type testing. Okay, so there's a very quick picture of in a lab environment. So you've got the source on the left-hand side, you've got the loopback, and then you've got the power meter on the right-hand side. And this is a USB one that's connected to a PC. So tier 2 testing includes an OTDR. So an OTDR, as I'm sure most of you know, stands for Optical Time Domain Reflectometer. It sends out a pulse of light, and it looks at the reflections from different events, and it looks at the timing of those reflections, and based on the timing, it'll tell you exactly where that reflection is. And depending on the level of the reflection, it'll tell you the amount of reflection in that event, and also the amount of loss in the fiber itself. So first thing to do is, at the top of the tower, inspect the connectors, connect in a loopback, because the OTDR test is typically done from the bottom. Often people, rather than using a loopback, will instead put a patch cord in place, maybe a 10-meter patch cord. Now the reason for that is if they have a 10-meter patch cord, they can look at both connectors. The OTDR will be able to see both connectors in that fiber pair. If they have just a loopback, those two connectors, a short loopback, those two connectors will just appear as one connector to the OTDR. The OTDRs have a dead zone. So they have a limitation as to how far apart the connectors can be. So people are typically using 10 meters, and that's a nice, safe value. So this is what it actually looks like. So the OTDRs, often the OTDRs will also include a fiber microscope, and certainly ours do. So you can plug a fiber microscope in here, and you can do a certification of the connectors using the OTDR display and store the reports on the OTDR. They'll also often include a light source and a power meter, and also a visual fault locator as well. So you send out the light out through a launch lead. You would typically use maybe a 10-meter launch lead or a 20-meter launch lead. So again, you can see that first connect on the patch panel. You test the first fiber, the feeder up the tower, the transmit feeder. At the top of the tower, you have a loopback or a patch cord at the top of the tower. Then you have the feeder down the tower, and then if you want to see the connector at the base of the tower, you might want to put a receive lead, so it gives the OTDR a little bit of space to look at that final, rather than seeing that final connector as the end of the fiber. If you put a receive lead on, it would you'd be able to see that final connector and see the condition of that connector. Okay, so the OTDR does lots of different things. As well as doing inspection, it's an OTDR, and often they have light sources and power meters, so you can do insertion loss, and they often have a VFL as well. So this is a schematic of the trunk cable. So this is a 2-link shot. So it's both up and down links, and there's a 10-meter jumper at the top. So section A is the 10-meter patch cord, the launch cable from the OTDR to the BSC as the base station connector. Event 1 is the base station connector, so it has some reflection, which is the peak, and it has some loss, which is the difference between the slope on the left-hand side and the slope on the right-hand side. And then B is the riser fiber. You've got 2 connectors. C is the patch cord between the riser fiber and the down fiber. And then D is the fiber on the downside, and then E is the base station connector. Event 3 is the base station connector on the down test side. And then you've got a section of after event number 4, which is the 10-meter patch cord. So you can see that final base station connector. So a couple of things that you'll be able to see with an OTDR, and this is quite a nice picture of one that we actually took of a macro bend or a kink in the fiber. So this is on the riser fiber, and you'll see a macro bend is you'll see it as a loss event, but it doesn't tend to have a level of back reflection. In this case, there's also a bad connector at the top of the tower. Now, because they use a loopback here, the two connectors on either side of the loopback are actually kind of merged into one connector. Because on the macro bend side, which is event 1, if you shoot that at two wavelengths, then you'll be able to tell that it's a macro bend because the higher wavelength will have higher loss than the lower wavelength. Okay, so they've used a loopback plug here. Now, if they had a 10-meter jumper, you'd be able to see both those connectors individually. But what you can see here, there's a high reflection, which is a high peak, and there's a high loss. That typically means there's dirt on the connector, or there's an air gap between the connectors. So this is a problem connector that certainly needs to be inspected, definitely needs to be cleaned, and may well need to be replaced. Okay, so this is our dirty connector. Okay, so on the troubleshooting side, this is a very typical flowchart that we see for a tower troubleshoot. The first thing to do is inspect the connectors. You check the power on the baseband units and on the baseband units at the SFPs. If you don't have any power, then you have a problem with the baseband unit, and you revert to the your transport type testing. If you have power, you connect your transmit port and your SFP at the bottom to the up path. You then move to the top of the tower, inspect the connectors, check the power from the remote radio unit. If the power is okay, again, you move to the transport layer type testing. If you don't have any power, then you know you've got a problem with the cabling. So you might then want to do an OTDR trace. If you have a good trace, you have a problem with the transport layer. If you have a bad trace, then you have a problem with the cabling. So this is an actual example of an OTDR trace from the base station up to the remote radio unit. So what you've got here is a couple of connectors at the base. So you're seeing two connectors at the start, and then you're seeing a couple of connectors at the top. You've got the first connector at the junction box, and then the high reflection is actually the connector that's connected up into the SFP on the remote radio head. So it's an open end, which is what you expect, and you'll see at the end of the fiber, and you also see a high reflection event there as well. So 14 dB means that it's the end of a fiber. So OTDR traces can be a little bit intimidating. At JDSU, we get a little bit blasé about them because we're kind of used to them. But we're aware that many people are not familiar with OTDR traces. So we've developed, I think, an application called SmartLink, which is an application that sits on the OTDR, and it's rather than displaying the trace, it displays events as problems like connectors or splices or end of fibers as icons, and it also includes the acronyms used in the fiber to the antenna as well. So it's a dedicated application for based on the OTDR for construction and maintenance. So one of the key things that comes out of this is report generation. So to the installer, this offers quite a lot of protection. So it offers proof that the install is correct. So it transfers the responsibility. to the people that then turn up the tower. So it offers them proof that they've done it correctly, so they get paid. Then it offers protection in the event that there's a problem with the turn up. Well, at that point they know that the fiber is installed correctly. So once you get onto the transport layer testing, and transport layer is actually not my area, but I'll mention it anyway. That we do have a solution for doing Fibre and OBSAI testing. So it validates the configuration and the performance of the SFPs that are used on the baseband unit and the remote radio head, and it does a bit error rate test of the Fibre on the fiber link, and also the latency, the delay of the signal. So a couple of user cases that we've seen. So this is a user case that we saw actually in Asia. Now I'm not going to read out the whole slide, but what came out of this was that the installer would install the cabling on the tower, and then some days later the site engineers would then try to turn up the tower. So the two events are not done by A, the same people, and B, at the same time. So what they found is that the transmission occurs after the site initiation, and what they found is they got a huge amount of problems with this, because the contractors that installed the cabling didn't really have anything to do with the turn up. So what they found is that they did 250 different sites, and they had something in the region of 25 to 30 site failures. Now it says 25% failure rate, but this is obviously not true. There's something over 10% site failure rate. So this had to be reworked. So this was the fiber itself that had to be reworked. So it was a 40-meter tower. They had to get a 40-meter cherry picker, $2,500 a day, 3 days for a rework. So each time somebody climbed up the tower, it cost $1,500 to $2,500. So the contractor did not make any money on any of these sites. So what they did in the end was they invested in a tier 1 test solution, so inspection, power levels. They could then certify the quality of work as part of the installation process, and they avoided, next time they tried to do it, they avoided an awful lot of the free repair work that they did, because they could prove that the fiber installation was done correctly. Okay, so another case that we saw was actually a North American operator. Now clearly LTE is rather bigger in North America than it is in Europe at the moment. So you had the contractor that did the physical infrastructure install, and then the operator did the turn up and commissioning. So again, the fibers were not lit until the turn up. And what these guys had was actually a 40% failure rate, which is clearly a massive problem. So when they did the detailed audit, they found that the 3 classic problems, which were dirty connectors, macro bends, kinks in the fiber, and they had the wrong fibers connected to the wrong ports. They had mislabeled the fibers. So the contractors were not inspecting, they were not testing, they were not certifying their work. So what the operator then required is installation and test reports. So when they install the network up the tower, they required reports, so proof that they followed the proper procedures. So fiber inspection, OTDRs, and the failure rate dropped down to less than 5%. So I need to hurry up a bit here. But the typical tool bag at the top of the tower would be, this is an analog microscope with a power meter. So it includes this actually includes a VFL, a visual fault locator as well. So you have this microscope, inspection probe, display. sits over your shoulder or around your neck to do hands-free testing. There's an LC loopback or a 10-meter patch cord, some cleaning tools, and then the right tips and adapters for the this particular one was LC connectors. And then we have the equivalent digital product. So as well as doing, so it does the same thing. So it does inspection, as power measurement, but it is able to store the image, do pass-fail, and then create a report of the connector at the top of the tower. So you're able to certify with that. And then at the bottom of the tower, because it's rather easier to have a PC at the bottom of the tower, a very typical tool bag is the inspection probe plugged into a laptop. There's a USB microscope that also plugs into the laptop and uses the same software, so you can have a combined report of power and end face. You've got a light source to do the round-trip loss, and then a visual fault locator to make sure you've got the fiber continuity correct, and then the cleaning tools and test tips for the LC connector. And then tier 2 testing is basically the OTDR. So without going into too much detail, you typically will use we have the smart link function if somebody is inexperienced with using OTDRs, or you can just toggle that across to the full trace. You need a fairly short pulse, 2 to 5 nanoseconds. Trunk cables are quite short, and you'll need some 10 to 20 meter test leads, just so you can look at those front connector and the back connector. One thing we found that's really important is hands-free operation. So this particular OTDR comes with a case and a neck strap, and it also plugs into the microscope, so it gives you the pass-fail end face analysis and certification. So as well as doing fiber testing at JDSU, we actually, just to make you aware, and again, this is not my product, but it's worth knowing what else we can do in this area. So we also make products for wireless testing. So we have drive test tools for service coverage. We have base station analyzers. We have power sensors, the actual RF spectrum analyzers, the cable and antenna analyzers, and then performance of the cell. We also make a system for testing the wireless protocol. So we do have a broad range of products, not just for fiber testing, but for the wireless testing as well. So as a very quick summary, so how do you ensure successive installations for fiber to the antenna? Well, to maximize profitability, you want to reduce the amount of rework. And what we've really found is the certification side. So if you're an operator and you want to make sure your contractors do the installation properly, you need some kind of proof from them. You need some kind of certification from them. And this comes from doing the proper, having good standards for tier 1 and/or tier 2 testing. Having the certification also drives best practices. If you have, say, a microscope that gives you a pass-fail that's objective, it also instantly turns operators, the people who are installing the fiber, it turns them into instant fiber test experts. And then if you have a certified install, you know what the performance is, you know what the loss is, and you can rely on it for the future. Deliverability, it's absolutely key to have these things turned up first time. Having them fail and having to come back to them is painful, and it costs an awful lot of money, and it removes it means the project won't finish on time. Once these things start, typically there's very rapid deployment schedules that are required. And then on as a contractor, you also want to limit your liability. So you want to, rather than being called back to do free reworks. So if the cell site doesn't work, you have to ask yourself whose fault is it, and who comes back to do the rework. Well, if the original contractor can provide a report that says, when we left it, all the fibers were correct, all the connectors were perfect, then they will get paid for the rework because somebody else has actually caused it. So if on the contractor side, they can certify that their work is correct, then they can, as well as having a less returns, they can also get paid for rework as well. And then the other side is, if you've got dirty connectors, well, if you plug them into an expensive piece of equipment, if the connector is dirty, then you can damage the fiber interface on the component or the equipment you're plugging into. So it's a good idea to prevent that as well. So Carol, I think I've spoken for long enough. So there's a couple more slides.